Okay, so very succinctly, I want to show you guys two very salient, interesting phenomena that are being observed over these Poncelet triangles in the so-called homothetic family. So these are triangles that are interscribed between a pair of concentric homothetic ellipses. I'm actually picking a point P on the Steiner ellipse, on the outer ellipse, and I'm drawing the pedal polygon to this guy with respect to P, right? So I have a family of pedal polygons that I can watch. First phenomenon is the following. Let's draw the circumcenter of these pedal polygons. Here's a circumcenter, and the phenomenon is that over Poncelet, the locus of the circumcenter is a straight line. No idea why. If I move P around, I get a different straight line over Poncelet. Okay, so let's go ahead and place P, I don't know. And by the way, a question here is what's the envelope of these straight lines? I wouldn't be surprised if it is a conic. But that's quite nice, right? This cannot be an affine phenomenon because perpendicularity is not preserved over the affine group, and pedals require perpendicularity, right? So, but incredibly, over any affine transformation, the locus of x3 remains a straight line. Another interesting question here is what is the locus of x3 of a fixed Poncelet triangle as I change my affine, my stretching coefficient here. Okay, all right, so this is the first phenomenon. Second phenomenon, instead of drawing the pedal, let's turn this off, I'm going to draw the antipedal triangle. Now, this is a classical construction. The antipedal triangle is a triangle whose pedal, with respect to a point P, is the reference triangle. So let's go ahead and watch what this guy is doing. Is it, oh yeah, so let me move P so that this guy is more visible. Here's the antipedal of my reference blue over this Poncelet family. I want to show a very salient phenomenon. Let's draw the centroid of this triangle, the barycenter x2. For some reason, it is just a stationary point. What is x3 doing here? If I draw its locus, x3, which was a line before, is actually an ellipse here. Let me just make a quick parenthesis, go back to the pedal situation where x3 was a straight line. What is the barycenter doing here? It's actually not doing anything special, okay? So unless this is some interesting curve like a cardioid, but this is not a conic, right? So if I move P around, it could be that this is a family of cardioids, which would be a cool result in itself, right? So x2 in the pedal case is not sweeping out a conic, but in the antipedal case, let me move P so this becomes visible again. Two incredible things are happening, at least in my opinion. Number one, x2 is stationary for any P. I can place P anywhere on the Steiner ellipse, and I get a family of triangles with stationary x2, and x3 is actually a beautiful ellipse. Now, I would hazard to say, and there's a bug here in my code, if you actually did 1 over this number here, since in this case here B is bigger than A, you would get this ellipse to be the exact same aspect ratio as the pair, the homothetic pair. Let's confirm that. So 0.4762, 1 over that, 2.1 approximately, and that's exactly what we have up here. So yeah, so the locus of x3 of the antipedals is an ellipse. X is aligned, but not concentric, and of the same aspect ratio as the outer one. So I want to show you guys a couple of things here related to x2, which are quite incredible. What is the locus of the stationary x2 of my antipedals over all P? Right, so I can stop Poncelet, and I can just now jog P and track what x2 is doing. Why? This guy is actually locus of x, yes. So the locus of x2, not over Poncelet, but over P, is this ellipse, whose aspect ratio is identical to the originating ellipse. So that's quite nice. This is over P. And then a final phenomenon, which surprised me quite a bit. I'm going to show you guys the locus of the vertices of this guy here over P. Okay, so the locuses of these vertices over P. So interestingly, let's turn off the label for now so we can see this better. And maybe I can make this guy a bit less eccentric so we can focus on what's really happening here. So as I vary P, the three vertices of my antipedal, each one of them is walking on a distinct cyan curve or light blue curve here, right? If I stop P somewhere and I jog Poncelet, x2 stays constant, and the three loci of each one of the vertices changes. Okay, so the first remark here is that numerically, each one of these loci is an ellipse. Okay, each one of these ellipses has the same aspect ratio as the original black ellipse, and all these four ellipses meet at a point right here. So if I move P around, okay, you can see here that the locus of x2 is the orange ellipse, and the locus of the vertices is each one of them a separate ellipse, and that these four ellipses that are on the screen here all have the same aspect ratio and are axis parallel to my original black ellipse. Okay, now just to top it all off, the sum of the three areas of the blue ellipses over Poncelet, because they're going to change now if I jog my Poncelet, that sum is invariant. So if you take the areas of each one of those ellipses, A times B, okay, which is variable, right? Their aspect ratio is invariant, but the product of their minor semi-axis A and B will be variable for each one of them. But if you actually sum them and you look at that numeric value over Poncelet, they are magically constant. That sum is magically constant. Okay, guys, so I wanted to show you these effects, and I'll see you in the next video. Thank you.